Here are solutions to homework set number 11 for ECE 376. This homework set looks at Z-transforms and digital filters. Now the first problem is actually Laplace transforms. Given a transfer function S relating x and y, what's the differential equation and what's the output for a constant and a sine wave input? Now the Laplace operator S assumes everything is in the form of e to the st. What that does is when I take the derivative, I get s e to the st. And so s means derivative. When I cross multiply, I get s squared y. What that means is the second derivative of y, plus 7sy, 7 times the first derivative, 18y, 6 times the derivative of x, 3 times x. So that differential equation corresponds to that transfer function. So anytime you see a transfer function in S, think differential equation. The reason we do that is it makes part B pretty easy to solve. I just use superposition and phasors. This is a linear system. What linear means is that f of a plus b, try it again, f of a plus b is f of a plus f of b. That's the definition of linear. So given this problem, I have complex input. I'm going to treat it as two separate problems. So here's A and B. Find the output when the input is 2. Find the output when the input is 3 sine of 4t. Add the two answers together, I get the total answer. So this is how you implement it. That's how I analyze it. The way I implement it, I just take the net waveform, run it through my filter. Analysis is using superposition phasors. Treat it like two separate problems. So the first problem, if the input is 2, everything is e to the st. 2 is just 2 times 1. When s equals 0, e to the 0 is 1, so s equals 0. The input is 2. This is the gain everywhere. All I care about is what's the gain at s equals 0 times the input at s equals 0 gives you 0.333. So there's the output when the input is a constant of 2. If the input is 3 sine of 4t, here s equals j4, that's my sine wave frequency. X is 0 minus j3, real part's cosine, minus j is sine. The gain everywhere is your transfer function. All I care about is what's the gain at 4 radians per second, times the input at 4 radians per second, gives you a complex number. Real part's cosine, minus j is sine. Put the two together, I get the DC term and the AC term, part A, part B. Total answer. And kind of a comment. The mistake students oftentimes make is they'll take the two answers, DC and AC in phasor form, add them together. You can't do that. The DC term represents this part. The AC term represents this part. This doesn't simplify. I can't say 0.33 plus 0.13 cosine is 0.19. That's kind of nonsense. You can't simplify the two terms. You've got to treat it like two separate problems. Okay, that's in the Laplace domain. In the Z domain, it's really about the same thing. What the Z transform assumes is everything is in the form of z to the k. So if I go y of k plus 1, I get z to the k plus 1, which is equal to z times z to the k, which is z times y. So in the Z domain, z means next value. If I have a transfer function in z, that's a difference equation. Multiply everything out, cross multiply, and what it means is z squared y is y two samples in the future. That's a z. zy is one sample in the future, current value. Zx is one sample in the future, current value. So there's the difference equation that corresponds to that transfer function. So anytime you see a transfer function in z, think difference equation. Where that's useful is if I have a problem like this, same as we did back in the S domain, treat this as two separate problems. When the input is 2, x equals 2, s equals 0, the conversion to the S plane is z is e to the st. We're going to be using that over and over again. That's the thing you got to memorize for the relationship between S plane and Z plane. Z is e to the st. So when s equals 0, z is 1. Here's the gain everywhere. I just care about the gain when z equals 1 times the input at DC gives you a number. So there's the output at DC. When the input is a sine wave, x equals 0 minus j3, 0 cosine, 3 sine. S is j4, z is e to the st, which is e to the j.04. This is where TI calculators really struggle. HPs work just fine, MATLAB works just fine. I want to analyze this at z is e to the j.04 at a complex number, times the input, I get a complex number as the output. What that means is real part's cosine minus j is sine. The total answer then is DC plus AC. Finally, in part C, if I have a step input, this is the gain times x, replace x with a step input, and there's to be 2 times that. I missed a 2. So there's your step input. This isn't in my table, so let's do partial fractions. I'm going to pull a z outside. Now do partial fractions on the inside. Multiply through by z. Take the inverse z transform. There's the DC term. 0.9 to the k, 0.4 to the k, and I forgot a 2. So the answer should actually be double that. Problem 3. Designing filters in the z-plane. So if I have g of s, come up with a discrete time version of g of s. And again, the conversion is z is e to the st. I've got 3 poles in the s-plane. I've got 3 poles in the z-plane. I've got no zeros s-plane. I've got no zeros z-plane. So it's just kind of one-to-one mapping. I've got a pole at minus 4 in the s-plane. In the z-plane, its map is e to the st. This becomes 0.9608 in the z-plane. Minus 7 becomes 0.93. Minus 10 becomes 0.90. So there's my filter in the z-plane. The gain k just matches the gain at some frequency. So pick your favorite frequency. I like DC. At DC, the gain should be 1.78. Pick k, so this also has a gain of 1.78. I'm doing some algebra. You plug in z equals 1, solving for k. K is 0.00045. So there's g of z. This is actually pretty common. What that 0.0045 means, if I take the step response, now this is going to do something like this. In 10 milliseconds, it doesn't change by a whole lot. That's the 0.00045. Eventually it does change, but that takes time. So if you see a small number like that, don't panic. That's very typical. To check, if the two filters are the same, they should have the same gain versus frequency. So plotting the gain from 0 to 30 radians per second, S is j omega, is my sampling rate, z is e to the st, here's g of s, there's g of z, plot g of s in blue, g of z in red, and what you see is basically the two match up so well, you can kind of see a little bit of blue sneaking out in the background. The two filters are so close, you really can't tell the difference. So from a user standpoint, I don't know, I don't really care how you implement it. I could implement it in the S-plane, that'd be an op-amp circuit with capacitors. I could implement it in the Z-plane, that'd be a microprocessor and a program. Input-output, they look the same. If I have complex poles, same story. I've got 3 poles S-plane, I've got 3 poles Z-plane. One pole's at minus 4 in the S-plane, maps as 0.96 in the Z-plane. Another one's at minus 2 plus J9 S-plane, maps as 0.97 plus J.09 Z-plane, and the conjugate. Optionally, I could multiply all this out, get real coefficients, your choice. To find k then, match the gain somewhere like DC. The DC gain of g of s is 1.25. Pick k to make the DC gain also 1.25. And here k is 0.00048. So there's g of z. As a check, plot the gain versus frequency for g of s, gain versus frequency for g of z, and the blue line is g of s, the red line is g of z. Again, you can kind of see they are basically identical. So from user standpoint, I don't know, I don't care how you implement it, S-plane or Z-plane. It's the same filter. Problem 3 is the reason we like Z-plane is it's really easy writing programs to implement that. The trick is, given the transfer function, multiply it all out, cross multiply, note that Z means next value, do a time shift, that's a change in variable, shift everything by 3, solve for y of k, and there's your program. So this is the difference equation corresponding to that transfer function. Actually, all three of these are a difference equation. All three are perfectly valid difference equations for that transfer function. This one's nice for a program, though, because what I do is I record the current input, remember the last three inputs, remember the last three outputs, and here's your program. The current output is 2.9 times the output one sample ago, minus 2.8 two samples ago, plus 0.9 three samples ago, plus 0004 times the input 3 samples ago. So that's actually really easy programming this. That's why we like Z-transforms. Z-transforms are really easy to program. So if you're dealing with a program, you really should be using Z-transforms. If you're dealing with an op-amp circuit with capacitors and inductors, that's Laplace transform. Problem 6 looks at something kind of neat called an FIR filter. The idea is that time and frequency are related. If I know the time response, I know the frequency response. If I know the frequency response, I know the time response. If I have a filter like this, can I specify the impulse response? If I know the impulse response, I know how to implement the filter using a thing called an FIR filter. So the first step is come up with the impulse response of this filter. So to do that, I'm going to actually do rectangles. In the lecture notes, I know that a filter with a corner at 1 radian per second is 1 over 2 pi sine of t over t. If I scale it to x pi, then it's times sine of xt over t. Make a bunch of low-pass filters. So here's one. The second one, let's do that one in green, is add that to this filter. So I'll add that one. Then I'll have to subtract out this part. That third one, let's do an orange. I'll subtract out 0.5, this guy. So there's a minus. So add these two, the green and blue, subtract the orange. Well, that B is 0.25 times the low-pass filter with a corner at 7, plus 1.25 times the low-pass filter, corner at 5, minus 0.5 low-pass filter, corner at 3. From the lecture notes, that's just a sinc function, sine of 7t over t, sine of 5t over t, sine of 3t over t. So pick your sampling rate. I'm going to choose 1 millisecond. If t goes between minus 30 and plus 30 seconds, shift it slightly to avoid dividing by 0. This is your H1. I want the DC gain to be 1. So if I add up all the terms, I should get 1, and I'm off by pi. So I actually need to divide each of these by pi. Not too surprising. Pi seems to show up pretty often. So there's my impulse response. That allows me to design my FIR filter. I just add all three of these up, and that's my impulse response. If I want to find the gain versus, well, if I plot the gain, trying again. If I plot the impulse response, let's plot t versus impulse response, that's what she looks like. This should go from minus infinity to plus infinity. That's kind of hard to do, so just to make it approximate, let's go from minus 5 to plus 5, and let's use 100 points in that region. So here's my approximation, going from minus 5 to plus 5. Sampling rate is 0.1 second, giving me 100 points. There's my filter. That's what she looks like. Problem 8 then is, given my filter, plot the gain versus frequency. So let's plot it out to 10 radians per second. S is j omega. There's my sampling rate t. Z is e to the st. The gain is just my tap delay line, the impulse response at t equals 0, delay by 1, delay by 2, delay by 3. Take the impulse response times z to the minus I. and z is e to the st, e to the j omega t. Add them all up, and I get this. So the blue line is my approximation. Okay, not great. Okay. If I did a few more points, let's go from minus 20 to plus 20 seconds with 800 points. That matches up better. That's the power of an FIR filter. I can implement pretty much any filter that I want as long as I can specify the impulse response. And you can get a pretty good filter. The cost is I have an 800th order filter. I need to do 800 floating point multiplies, 800 floating point adds. A little bit much for a PIC processor, but not a problem for DSP. So that is homework set number 11 for ECE 376.